Good morning, everyone. Acute intermittent hypoxia, or AIH, is a safe and non-invasive treatment approach involving brief, repetitive periods of breathing reduced oxygen air, alternating with ambient room air or normoxia. Induced oxygen can be delivered using a hypoxic generator, as shown in this diagram, and AIH-induced changes on motor cortical excitability can be quantified using a non-invasive brain stimulation technique called transcranial magnetic stimulation, or TMS. This diagram shows the basic principles of TMS. Essentially, neuronal activation in the motor cortex travels down the corticospinal tract through peripheral nerves, ultimately reaching the target muscle, where it generates a motor-evoked potential, or an MEP, which can be used as a measure of corticospinal excitability. Current evidence suggests that there are physiological benefits of AIH exposure in patients with spinal cord injuries. A recent study in 2018 exposed 20 male participants to 30 minutes of AIH with a fraction of inspired oxygen set at 9.4% in a 1 minute on, 1 minute off pattern. TMS measures and measures of spinal synaptic excitability were taken before and at 5 time points after exposure. This study found that 30 minutes of AIH exposure increased corticospinal excitability for up to 75 minutes after exposure. The study also proposed that changes in corticospinal excitability were likely related to synaptic plasticity, and therefore the cortical effects of AIH are still largely unknown or unaccounted for. The aim of this study was to examine whether exposure to AIH alters corticospinal excitability and the excitability of intracortical inhibitory and facilitatory processes within the primary motor cortex. 18 participants took part in 2 sessions. AIH was delivered in 1 session and comprised 3 minutes of hypoxia, with a fraction of inspired oxygen set to 10% and 2 minutes of normoxia at 21%. This was repeated over 5 cycles. Normoxia was delivered in the other session. In each session, TMS measures were taken before and at 3 time points after the intervention. Session order was counterbalanced across participants. Arterial oxygen saturation levels, or percentage SpO2, were measured in both the hypoxia and normoxia sessions to establish the validity of the hypoxia induction protocol. There was a cyclical reduction in SpO2 levels in the hypoxia condition and little to no change in SpO2 levels in the normoxia condition, as expected. This figure shows the MEP amplitude elicited by single pulse TMS. As we can see, MEP amplitude was not different at the 4 time points and across both sessions. Single pulse TMS was also used to generate an input-output curve by delivering TMS stimuli at increasing stimulation intensities. This measure was used in addition as it reflects the states of corticospinal excitability in a more comprehensive manner by probing a larger population of neurons within M1. Whilst there was an increase in MEP amplitude as a function of increasing TMS intensity, as we would expect for this measure, there were no differences between input-output measures at the 4 respective time points after exposure to AIH or normoxia. Collectively, these measures suggest there were no changes in corticospinal excitability as a result of AIH or normoxia exposure. Intracortical inhibition was measured using the paired pulse TMS protocol, short interval intracortical inhibition, or SICI, which likely reflects GABA-A mediated inhibition. SICI was quantified by expressing the mean conditioned MEP as a ratio of the single pulse mean MEP. Ratios less than 1 indicate inhibition. Whilst inhibition was seen at all time points, there was no interaction between time and condition. We observed that SICI decreased over time, as shown by this asterisk, but this trend was seen in both sessions. This suggests there were no changes in SICI and hence no changes in GABA-A mediated inhibition in the primary motor cortex. Intracortical facilitatory circuits were quantified using the paired pulse TMS ratio, intracortical facilitation, ICF, and short interval intracortical facilitation, SICF, with 2 interstimulus intervals of 1.5 and 4.5 milliseconds. For these measures, ratios greater than 1 indicate facilitation. ICF is suggested to be a facilitatory circuit modulated by glutamatergic-mediated processes, while SICF is believed to be mediated by I-wave summation processes. Both SICF and ICF remain similar at the 4 time points and after exposure to either hypoxia or normoxia, suggesting that there were no changes in intracortical facilitatory circuits that are mediated by either glutamatergic or I-wave summation processes within the primary motor cortex following exposure to hypoxia. A key consideration in this study is whether the hypoxia dose used was sufficient to induce changes in motor cortical excitability. The earlier 2018 study used a protocol of 1 minute on, 1 minute off at a hypoxic fraction of inspired oxygen of 9.4%, whereas in the current study we used a 3 minutes on, 2 minutes off protocol at a hypoxic fraction of inspired oxygen of 10%. During the hypoxia session, there was large inter-individual variability in terms of the magnitude of reduction in SpO2, ranging from 76% to 97%. There were some individuals that did in fact show cyclical reductions in SpO2 that were in line with the AAH protocol, while some individuals did not show changes at all. Bivariate correlation analysis shows that there was no significant relationship between an individual's oxygen saturation, as shown on the x-axis, and normalized MEP amplitude, as shown on the y-axis. Whilst not statistically significant, there was a moderate negative trend between SpO2 and MEP amplitude in the hypoxia session, whereby those who showed the greatest hypoxic response showed the greatest change in MEP amplitude. This suggests that the dose of hypoxia used in this study was not sufficient to induce hypoxia in all participants and may attribute to the lack of changes observed in corticospinal excitability at the group level. Overall, this study suggests there were no changes in motor cortical excitability following exposure to acute intermittent hypoxia. Given that AAH has been shown to improve function in spinal cord injury patients, future research is required to determine the potential of AAH in neurorehabilitation. Future technological advancements may allow for clamp-based studies whereby the level of induced hypoxia can be controlled individually, thereby reducing the variability in responses, and also to incorporate specific measures of spinal cord excitability. Other avenues of future research may involve testing a wide variety of AAH protocols on both younger and older adults and in clinical and healthy populations. Thank you.